Polyphase. In the US, we use a three-phase power supply. When you look at the power line in the street, you'll see these three wires going in and maybe one ground there. We use a three-phase because we found out there's a distinct advantage to that, to using the polyphase. First, in terms of the machine, we can also just rotate the three-phase power instead of just one single phase. Here's what happens when you have a single phase power supply. This is what your source looks like. Then it goes to zero, then it goes negative, then it goes to zero, then it goes negative, then back to zero, and so forth. By using a three-phase system, and if you're using a three-phase system, this is a sine wave, right? How long it takes to complete a sine wave? What's the period for a sine wave? 360 degrees, right? It takes 360 degrees to complete itself. So what's 360 divided by 3? 120. So we use three sources there. Instead of one, we use three. They all operate where the first one has a value of 120 angle 0. Now the next one is going to have a phase shift of 120 degrees. So the next one will start here. And the next one is going to be another 120 later, which is what? 240. So 120, this is angle 240. This one should be 120 here. We'll talk about positive and negative, the value. But this one starts 120 degrees later. So notice that's lagging the way my picture is. 120 negative. We'll talk about positive versus negative. And this will be a negative 240. Just from the picture there.
Does the first one just represent like the sine wave? Is that your...
The first one is the sine wave, yes.
No, the top one.
Yes, the basic sine wave. This just sine. Let's say 120 sine WT. So what's going to happen, instead of your source now going back to zero and switching to negative, so imagine if this is a motor, it's spinning positive, it's going to stop, reverses direction. Well, now we're going to supply it with this. So it's going to ride on the top of that. So it's going to ride like this. And the minute it starts to get to this point, it wants to continue going down, the second one comes in. Then the next 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 one, continuing that pattern. So actually you're working on the top portion of that function. You're not letting it go back to zero and reverse its direction, where if you use a single motor there, it's going to spin, change direction, all that. And that's easy actually to create in terms of equipment. So a three-phase system is not uncommon here, especially in manufacturing. You know, we use that all the time for large refrigeration system, machinery facility, three-phase wired. When you see the power line come into your house. Now, we're going to be talking about a system has a balanced three-phase. Now, what does that mean, three-phase? They're all going to be off by 120 degrees. That's a balanced one. The source has three terminals, has three wires coming out of it, and they're all off by 120 degrees. And usually you have, not counting the ground, we don't count the ground, but we have three sources, three wires plus the ground. And they are all off by 120 degrees. That's what we mean by a balanced system. Sometimes you have a system at 120 angle 0. This is 120 at 90 degrees. This is 120 at 225. That's not a balanced system. That's not a balanced source. A balanced source, all these angles going to be off by 120 degrees. If we use a four-phase system, four-phase, instead of three, what's 360 divided by 4? 90 degrees. So the first one will be 120 angle 0, 120 negative 90, 120 negative 180, 120 negative what? 270. So it depends on the number. And the load, again, we try to use a balanced load, because once you do the calculation for 1, you multiply it by 3, and you have your answer. Now, people said, well, why not even use 6 phases instead of just 3? In the US, we found out the ultimate number is 3 phase for us. If we use 6, 8, 9 phases, you're staying almost DC. You're staying really high up there. Sounds like a wonderful idea. To use that, we still do actually 6 and 12 phase system, but not in everyday use. We use that where? 12 phase. Imagine if this was 12. This is what's going to happen if this was a large value. So watching the first one, it looks like this. And start to go down. The minute start to go down, the other one comes in. Then the next one comes in. Then the next one comes in. What do you have now? If you have multiple phase, more than 3 phase, like 4, 5, 6, 7. So, exactly. It starts to react or work as a DC. That's actually where we use it right now. We use 12 and higher number of phases if I want to create a DC, a direct value that's constant. We use multiple phases. So this approximates usually an ideal voltage source, let's say of 120 volts, if that's what you want to get. Now, let's talk about these 3-phase systems. We're going to talk about them. We label them A, B, and C. So this is a 3-phase system. This is the neutral, the ground here. We have 3 phases in it. We'll call the first one A. Notice minus here, plus there. That's not a 12, that's an AC value. That's A. We have, this is minus, this is plus. That's B here. And the third one, minus, plus, and that's C. So this could have 120 angle 0. Then B will be what? 120 negative what? What's the phase shift? 120 degrees. Remember, 360 divided by 12. And this one will be what?
Negative 240.
120 negative 240. And you might see us write that instead of negative 240 as what? Positive 120. That's the same angle, right? Actually, that's B here and C. I just had them backward. This is B and this is C. B is the next one. That's the 120. A, B, C. We just go in order. A is the first one. B is the second. C is the third one. When you connect them like this, if you put them standing up, I usually draw them standing up. I don't like the way I'm drawing them here. I will draw them a lot of times like this. This is A. This is Vmax, could be RMS, whatever, angle 0. This is Vmax angle what? Negative 120. This is Vmax angle negative 240 or plus 120. I draw them like this. We call that configuration a Y. It looks like a Y upside down. You can even reverse them, make them look like a Y, normal Y. So don't be surprised to see these drawn multiple ways. Don't be surprised to see it looking like this. That's why it's called the Y configuration. All of these means the same. Vmax angle 0, Vmax angle negative 120, and Vmax angle negative 240. That's why this is called the Y configuration. Y connected. So you'll hear us talk about the Y versus delta. In most actually books, especially in our book, a lot of times the way they connect them, they look even different than that. They might connect them this way. I'm just getting crazy with it now. This is A. This is the neutral. That's N. This is B. And this is C. That's the same thing. Doesn't look like Y. I like that one better because that looks like the letter Y. This doesn't look like it, but that's also known as a Y source there.
As long as the negatives are going to the neutral.
The negative always going to neutral, always. All three of them. So this is Vmax angle 0, Vmax angle negative 120, and Vmax angle negative 240. All of these represent a Y source, a balanced Y connected source. Balance. All of them. Y connected source. And the book will say source, Y source. It talks about Y versus delta because they look like the letter Y. So sometimes you attach to that a load that's also a balanced load. A balance, that means all the values are the same. Now, one thing about that source, when you look at it, doesn't matter which one you look at, right there. If you take all these values and add them, let's have fun with this. I like this one. I like the one that looks like Y. So let me draw that source and just have fun with it. So I'm going to go back, just the one that looks like Y. Vmax could be any number. This is A. This is B. Vmax angle negative 120. And this is C. Vmax angle what? Negative 240. What do you think will happen if I go mathematically? Do the math. If I add the three sources together, what is the value going to equal to? What's VA? We call this, by the way, VAN. We call this voltage VBN. And we call this one VCN. If I take VAN, add to it VBN, add to it VCN, what is that answer equal to?
360.
Let's see. Here's my calculator. So this will be what? Vmax angle 0 plus Vmax angle negative 120 plus Vmax angle what? Negative 240. I can factor Vmax out. What's left? 1 angle 0 plus 1 angle negative 120 plus 1 angle negative 240. I have a feeling that this will be what?
1 angle 30.
Are you sure?
I don't know.
I don't know, Mal. I'm thinking maybe it's a 0. 1 angle 0 plus 1 angle what? Negative 120 plus what? 1 angle negative 240. It's 0. If you add all three sources, 0 times anything, that's a 0. I know why you said that. So I'll give you an answer to your question. I can read your mind.
Can you?
Yes. What about if I want to measure the voltage between A and B? It's not much to read his mind. There's nothing there.
Oh.
Yep. If I want to read the voltage between A and B, meaning what? If I take a source, this is the source. Not a source, I mean the power, the digital multimeter. We're going to measure the voltage there. What is that source going to read? What's the meter they're going to read? If I said, let's connect a meter, the plus here, the minus there, and tell me what the meter is going to read. It's not a source, so it's a meter there. So let me make a box there instead of a circle. So this is actually the device that we're going to use to read the voltage. What do we read there? This voltage here, since the plus here, minus there, is known as VAB. So if I do KVL inside this little triangle, if you travel inside this triangle, what are you going to see? VAB plus VAB, right? I'm going plus to minus as a plus. Some people use minus, I'll use a plus. Plus VBN minus what? I mean VBN, yeah, minus, what's this voltage here? VAN is equal to 0. That tells me VAB equals VAN minus VBN. So let me take my calculator out and let's do some math. Let's find out what VAB is. It's Vmax. We can factor that out. It's 1 angle 0 minus what? 1 angle negative 120. And let's see what do you have there. What is 1 angle 0 minus 1 angle what? Negative 120. Now let's change it to polar instead of rectangular. And let's do the calculation one more time. 1.73. What is 1.732? That's the square root of 3. And what's the angle? 30 degrees. So if you know what VAN is, if in this case we know what VAN is, Vmax, the square root of 0, guess what VBN is going to be? VBN is going to be the square root of 3 times Vmax, and the angle will be 30 degrees. You're always going to multiply, by the square root of 3, and you're always going to add 30 degrees to that. And if your source is a balanced source, I can do the math for VBC and VCA. I can do it for VBC right there.
Wait, shouldn't that say VAB equals square root of 3 VM?
VAB, yes. I wrote what? BN?
Yeah.
No, VAB. So basically, it's VAB equals the square root of 3 times VAN, and also add to it angle 30 degrees, or let me just write nicely there. Like this, times VAN. When you multiply that, whatever VN, you multiply the magnitude by the square root of 3 and you add 30 degrees to the angle. So what about if VN does not have a 0 for a phase here? Let's take an example. Let's assume, on the next page, Okay. And while I'm at this, what do you think VBN is going to be? I mean VBC. If everything is balanced, all these sources are equal with 120 degree phase shift, then the voltage here, VBC, will be the same as VAB except what? Shifted by 120 degrees. So what is 30 minus 120? Would be negative 90, right? So it would be the square root of 3 angle negative 90 degrees times VAN.
Does that mean it's like imaginary?
Which one?
I don't know, negative 90, right?
Yep, I'm going to play with the math in a minute there. And what's the voltage VCA? Not AC, I'm traveling this way. What's VCA? Bless you. So again, this source here will be what? 240 off the first one. So what's 30 minus 240? Is that negative 210? So once you know actually what VAB is, subtract from it 90 degrees to get VBC, subtract from the angle another 120, subtract, I mean 120 to get VBC, subtract another 120 to get VCA. Let's take an example. I'll leave it on the same page. Assume, to make sure you understand it, that VAN is equal to 7 angle 23 degrees. I just picked a crazy number. What is VB, what is VAB then? Is going to be the square root of 3 angle 30 times 7 angle 23 degrees. 7 times 1.732, 7 times the square root of 3, turn it on first, 7 times the square root of 3, this will be 12.12, and the angle, when you multiply, you add these values. I don't have to do the calculator, I know I can do it in my head. That's what, 53? Once I know VAB, can I find VBC? Yes, what is it? It's the same value except what? This angle here is going to be this one minus 120. 53 minus 120. What's 53 minus 120? Negative 67. Can I get VCA? Sure. It's going to be the same value, but instead of 53 minus 120, it's 53 minus what? 240. That's what's nice about being balanced. If it's not balanced, then I got to do the math the way I did right here. I got to take each value and go through them. And maybe I'll give you an example that's not balanced in a minute. What's 53 minus 240? Is that minus 187? So if it's balanced, once you know one, just go through and calculate the other ones. Just subtract 120 to get the next one, subtract another 120 to get the third one. Done, quickly. If your sources are not balanced, these sources are not balanced. Let's take an example on that. Then you just got to do more math. The rules don't change, but just more math. Let's say this is 10 angle 30 degrees. That's A. This is B. Let's say 15 angle 92 degrees. And this is C, which is 17 angle, I don't know, 119 degrees. So that's not a balanced source. Then if you want to find VAB, from here to there, it's VAN minus VBN. Remember, this value is known as V, this is N here. By the way, for the source, we always use lowercase letters. For the load, when we get to the load, we're going to use uppercase. So this is VAN, all lowercase. This is VBN. This voltage is VCN. So again, if you put a device here to measure the voltage, what is that value here? What is that number? I want the plus on this end, the minus on that end. So that's traveling this way. It's this voltage, you're going plus to minus, that's minus to plus, that's why you subtract that. So now that would be what? 10 angle 30 minus 15 angle 92. It's not going to be the square root of 3. It's not going to be 30 degrees off that one because it's not a balance. All the rules only I showed you there for a balanced when your source is a balanced source. If it's not a balanced source, we can't use the square root of 3. We can't just add 30 degrees. We just have to do the math. Ten angle 30 minus 15 angle 92. And that's 13.6 angle negative 47.4. And if you know VAB does not help you finding VBC. That does not help me at all because it's not a balanced source. So to find VBC, B is the positive, C is the negative, that's VBN, minus, because you're going this way, minus, this is plus to minus, this is minus to plus, minus VCN. That's why it's nice to be balanced. I can do the math much quicker and easier. Once I know one, I know the other two. Not here. 15 angle 92 minus 17 angle 119. The result is 7.72 or 7.7 angle 0.9 degrees. And if you want to find VCA, C is the plus, A is the negative, that's VCN minus VAN. Going this way. I'm putting the plus on this end, on the bottom, the minus there. So this in the same direction, that's backward. So it's 17 angle 119 minus what? 10 angle 30. (17 angle 119) minus 10 angle 30 degrees. So you end up with 19.6 angle 149.7 degrees. None of these guys look like 120 degrees off the other one. And if you add the three sources, I guarantee you it's not a zero. This is not a balanced system.
Can we sue the electrical company?
Well, we're going to be dealing with balanced systems, so don't worry. Almost all our calculation is going to be a balanced source, balanced load. Once in a while, the load is not balanced, but the source is balanced. So we're dealing with balanced sources. But every once in a while, here and there, you have something that's not balanced. If it's not, you got to go through the math like this. Now, I was looking for a statement here. Can't find it quickly. Okay. Now it says, almost without exception, polyphase systems in practice contain sources which may be closely approximated by an ideal voltage source. We make an assumption these sources are ideal, or by an ideal voltage source in series with a small internal resistance. There's a small resistor there that we neglect. Three-phase current sources are extremely rare. You will not see them. But you see three-phase voltage source, not three-phase current source. In the US, extremely economical to operate a three-phase source. That's why we use three-phase. We did some work on them based on the cost and to make them and what we're getting for power and everything. We found that ideally three-phase system is the best or ultimate way for us. Just like we operate 120 volts at 60 hertz. You go to Europe, it's 240 at 50 hertz. You know. But in the US, we did our work, and we found out this is really where we need to operate to be more efficient. Yes?
Have you ever seen a three-phase current source for in use?
We don't, three-phase?
Like current source?
Oh, no.
No.
Me, personally, no. I never seen it, no. Well, I want to say three-phase voltage source, you see with a power supply, just look up there, you know. But I've never seen a three-phase current source, no. Sometimes you don't have to have a three-phase. You might be in the lab and you need a two-phase. I'll just give an easy example. At home, let's say you just bought electric electric stove. To operate electric stove or dryer, actually, you probably dryer needs 240 volts, most of them. Some are 120, but most of them are 240. Yep, so how do you get that 240 volts there? You only have 120.
Tie together two 120.
Yep, you take one like this, which is 120, and you take another one now, and you do, the plus on the top, minus on the bottom. You're going to add them, right? I'm not trying to kill them. I'm trying to add them. I'm still thinking about the neutral. And there's another 120 here. So what happens when you measure between here and here? You have a 240. That's actually what they do. They take a 120, connect them. In the lab, when you're doing even DC, and you want to get a 10 volts, and your source is only 5 volts, and you have two of them, you can take a 5 volts here, and if you have another one that's 5 volts, if you attach it like this, what do you have here between this and that? You get the 10 volts. If you reverse that, so if I attach them like this between the top and the bottom, I have what? 240 volts now. If this is 120 angle 0, and this is 120 angle 0, when you add them, what do you have? You have 240 angle 0. And I got my 240 volts, now power supply. Yes?
Is this kind of like in relation to like transformers? Like for example, if you have like a step-down transformer on the secondary side, you have like a tap that can be half the voltage.
Well, I'm glad you brought that up. And step up and step down transformer. What chapter here? Chapter 13, the next chapter. Yep.
Well, coupling
Yep.
transformers,
You can step it up or step it down. When you have the power, if you live by a power line, the voltage on these power line is massive. Your house doesn't need 72,000 volts, you know? So we need to step that down to make sure you're getting what you get. Or if you live in a neighborhood that we anticipate is going to be 10 homes in that neighborhood, suddenly the planning board decide to sell that piece of land at the end of your property and put 20 more homes. Well, we need to give them power. What do you have at the end of your street now? It's not enough to supply power to the people we're going to be adding there. So that's when we have to beef up that voltage and the current going to them. And that's the step up and step down transformer. You know, you see them on these power lines all the time. two gray tubes, they're round ones, you know, because most houses have to, like, if you have 200 amp circuit breaker in home, you can tell if you have like one long board with two sides of it, that's 200 amp. If you have a short one, that's 100 amp. Well, if you have 200 amps in your house, you actually have one side, another side, have two sides, the left side and the right side. If you look outside, there's two transformers there. I can tell you when we had that snowstorm in my house, I lost power in half my house. I called them, they said, oh no, it's your house, nothing to do with us. The power company was there. Well, lucky for me, my neighbor came out, before I called my electrician, my neighbor came out, and he goes, hey, I only have power in half my house. I go, so it's not my house. Then they realized one of the transformer blew. So the left side of the house was not working, the right side is working. But then you have two of them actually coming in. So now, do we have time to do it? Nope, out of time. We'll do more with these next video.